Hello, students. Today we want to talk about the limit of a real valued function, at least in terms of algebra, intuition, and then a formal definition. And then following this, in another lecture, we will talk about how we can compute limits analytically, looking at them like objects and then applying different rules depending on the objects that we see to compute limits. So the idea of limit is something that carries through the entire calculus sequence. It's very important. And just remember, though initially the going might be a little uneasy in terms of understanding all the nuances of the definition, it's basically lots of arithmetic. So it's a very straightforward arithmetic if we can put the pieces together. So what I want to do first is to just share an intuitive example with you, because I think it helps if we can look at an example that we've seen before in pre-calculus. And what you're going to find as we go through calculus is that we use large amounts of college algebra, large amounts of pre-calculus, and that would include exponential, logarithmic, trigonometric functions, sequences, all of that material. So you'll start to realize why you studied the courses you did that preceded Calculus 1. So what I want to do is start with a function that you have seen in pre-calculus. You studied radicals and you studied quotients of algebraic function, so to speak. And so we would call this an algebraic function. Now, what I've written over here are two things. First, I'd say consider x approaching 0. You might look at that and think about that. And then I've written rewrite using a conjugate method. Now, just looking at the first item here, if we would think that x would get very close to 0 here, we would say the numerator would be approximately 0. And then, of course, x plus 1 would be very close to 1. And so if we have the square root of something close to 1 minus 1, again, that would be very close to 0. So what we have is really an indeterminate form. Let me write that word down, indeterminate. And this will play a large role in what we do in this class and in other classes, even in Calculus 2, as we develop other techniques for computing limits. So when we say indeterminate form, what we're saying is that the numerator is getting close to 0 and the denominator is doing likewise. Now, when we look at something like that, we just say, okay, well, indeterminate means we don't know. We don't understand division by 0. And so if we have 0 or approximately 0 in the numerator and 0 in the denominator, those do not absorb. They don't tell us anything. But what we can glean from something like this is maybe we have a function that has a hole in it. We remember rational functions where we would see that factors in the numerator and denominator would absorb and leave a hole in the function as opposed to a vertical asymptote. So many times when we see an indeterminate form, we're thinking there might be something else that's hidden that we can actually uncover. And here's what we're going to do. We're going to apply this conjugate method, and this will bring back some of the methods you used in trigonometry. So let's do that first. So we have x. I'll go ahead and write the function again. And now the conjugate. And when I say conjugate, we take the denominator and switch the minus sign to a plus. So we basically get a difference of 2 squares in the denominator. This is somewhat long-winded, but very useful. So if you like, you can use parentheses just to make things look a little bit more tidy, if you like. So again, when we say conjugate, we're thinking of like complex conjugate, again, where the minus is changed to a plus. So now in the numerator, well, we're not going to do anything with that except write down what we already have. We're going to let the algebra do the work for us. We don't want to work too hard, but we want to work smart. And now, of course, downstairs, we have the difference of two squares. Notice the outer and the inner products absorb. That is, I don't use the word cancel so much. I will say absorb because I prefer that word, and it may be a little strange at first, but trust me, as we work through the class, you'll get used to it. So when we do the outer and inner, those absorb. But of course, when we multiply the radical by itself, we just get x plus 1. And then, of course, -1 times 1 is just a -1. So that's very simple. Now, of course, the 1 and the -1 absorb, and we have x times the square root of x plus 1 divided by x. Now, at this point, what I usually teach my college algebra students in pre-cal is just use a little box. We just say that the x terms absorb. And I don't like using slash lines because that covers up your work, and that just doesn't make any sense to me. So let me adjust this a little bit. There we go. So at this point, we see that the x's absorb, and we're really trying to stay away from 0, but we're getting close to 0. I'll say more about that. So when the x's absorb, we get the square root of x plus 1 plus 1. Okay, so now we're thinking, all right, intuitively. Go back to what I've written initially, consider x approaching 0. So we would think, okay, if we just did a little number line and we had a 0 here, and we know this has to be fairly local. So for instance, we're approaching x from 0 from positive values and negative values. So this would be like a left approach, and this would be a right approach. So just so this makes sense, of course, we don't want the values of x to be too small because then the radical won't make any sense. So what we could do is we could just kind of restrict to say something like maybe -1/2 to 1/2. So we would start in that interval about 0, and on either side, from the right, we would be approaching 0 through positive values, and from the left, we'd be approaching 0 through negative values. So what our intuition is telling us, if that is indeed the case, and we know these are equivalent, that is, this is an identity. That is, f of x here is equal to the square root of x plus 1 plus 1 as long as x is not equal to 0. So we think to ourselves, if x is approaching 0, but it never quite gets there, but it gets arbitrarily close, then the value should correspond to what we get here. This is what we're thinking of as a function with a hole in it. As x approaches 0, the value of the function would then be the square root of 1 plus 1. Let me say a little bit more about that. So here's a notation that we could use. We could say limit, LIM short for limit, and then the approach bits, to make it a little bit more convenient, we could say x with an arrow, x approaching 0 of f of x. And so we'll have x square root of x plus 1 minus 1. Now, of course, we're using intuition here because we haven't developed any theory. I haven't even given you what the definition of limit is, but just thinking intuitively, which is how we start out, we could say, well, as long as x is not equal to 0, and let's just kind of make it very clear here, x never equals 0. That is, we get as close as you like using our little diagram here. And so this would give us the limit as x approaches 0 of what we found it to be, the square root of x plus 1 plus 1. Now, intuitively, we don't get this indeterminate form here. For instance, if x is approaching 0, then we could think of the square root of x plus 1 as basically the square root of 1, close to it, and then add 1 to that. So we're thinking, okay, if I just replace x with 0, I just get the square root of 1 here, and I add 1 to it, and I get 2. And I'm thinking, if there's a limit, if there's an actual limit, or intuitively thinking, then I would think the value would be 2. Well, at least for now, we're going to say that we think that the limit is 2. So if we were to sketch a graph of this function, at least near x equals 0, we would see that the graph would be approaching the value of 2, even though at 0, there would be no point. That is, at 0, the function is undefined. So the idea here is that the algebra we have done in this case is actually very, very important. But we need to know why we are doing it. We need to understand what is the limit, and why would we think that the limit would have to be unique? And if it were unique, it would, pretty much have to be 2. There's no way we could get around it, because as we think about our work in our previous classes, what's an identity? An identity is an equation that is true for all values of the variables for which it is defined. So if f of x equals this, we can simply say f of x equals this expression for all values of x for which it is defined. Just stay away from 0. And then we say, okay, well, if this is true, whatever we would think the answer would be here would have to correspond here. But the analysis of this expression, or this expression for the function as x approaches 0, is very clear to us. As you allow x to get closer and closer and closer to 0, x plus 1 gets closer and closer to 1, because you're adding something infinitesimally close to 0. So your intuition says the limit must be 2. So now let's move a little bit away from the intuition and think, if I'm going to compute a limit and x is approaching some number, and I can just substitute that number into the function and get something that makes sense, maybe I've hit the jackpot. And we would have hit the jackpot, but we need to know why that would be the case. And then in situations when we can't do that, we don't just throw our hands up in the air and say, well, I don't know what the limit is. We work with it, and we try techniques that expose the existence of a limit that may not be clear from the initial representation. So now that we thought a little bit about intuition, let's write down what we consider to be a formal definition, and then maybe look at some instances where a limit wouldn't exist. But we need a definition so we can feel good about what we've done here. So what does it look like? Well, let's go back to the same notation I had before and then fill in the arithmetic. So what we're going to say is the limit as x approaches c. So what we're going to say in this particular case, we'll just say c element of R is fixed. And when we say fixed, it's a constant. So C is a real number, it's fixed. F of x is a function. And L element of R is fixed. So we use L, uppercase L, for limit. Now, I've mentioned the fact that limits are unique, but we don't know that when we write down the definition, but keep that in mind. It will be the case. So what we want to do is to say that the limit of f of x as x approaches c equals L. We want to write that down like we did for the last one. So I'm going to put a box around this, because if you remember the last example here, what we had is a specific value for the c, a specific function, and a specific value for L. Okay. So now if we write this in a more abstract setting, what does that mean? Well, again, let me go back to this. We have to have some way of saying or describing that x is approaching 0 here, arithmetically, as I've diagrammed here. And then what it appears to be the case is that the function value is approaching 2. Okay, so that's what we want to say here. If the value of x approaches c, gets very close to c, then the value of f gets very close to L. And this is where we get to use absolute value. So now we'll have if and only if. And I won't use the logical symbolism yet. I'll go ahead and write out the terms, but later on we might be a little bit more flexible. So for epsilon positive, and this doesn't matter for any, and I'm just going to say for any. If you want to put any, you can, but for epsilon positive, that just says take a positive epsilon, and that just means any one you choose. There exists and we'll use the lowercase Greek delta. We have to get used to the Greek letters. So epsilon and delta, there's a positive delta such that, now, many times it will be the case that the delta will depend on the epsilon. But for right now, we'll just go forward with this. So for epsilon positive, there will be a delta such that, again, we use our absolute values. That is the absolute value of x minus c. That is, we're looking at the distance between x and c. If it is less than delta, but again, we're prescribing that x does not equal c by this absolute value or this distance being positive. So this greater than 0 is important. That basically says, as we said before, x was not equal to 0. Here in general, x is not equal to c. This will imply that we can make f close to L. So that will mean the absolute value of f of x minus L will be less than epsilon. So if you think about this, we probably wouldn't be too interested in situations where the epsilon would be too large. Okay, we're not, I mean, when we say for epsilon positive, we don't necessarily think of epsilon being that big. Maybe we choose epsilon equal to 1 for convenience. Maybe we choose it equal to 1/2 or 1/5 or whatever. The idea is that whatever value we pick, it has to make sense for the function that we are analyzing. So just keep that in mind. We say that the value of epsilon is arbitrary as long as it's positive, but with the understanding that it makes sense contextually with the problem. So how does this say this? Well, let's flesh this out. So now equivalently, we'll just use the absolute value. This will give us negative delta less than x minus c less than delta. Okay, again, this is just a conjunction. So now we have the additive inverse of delta less than x minus c less than delta, which implies we'll do the same thing over here. negative epsilon less than f of x minus L less than epsilon. So we're using a lot of the absolute value results from college algebra and pre-cal. And now we can say, if you want to add C to every side, we have C minus delta is less than X less than C plus delta. And that's giving us a little delta neighborhood like I did the negative 1/2 to 1/2 in the previous example. And then, of course, we'll do the same here. We have L minus epsilon less than f of x less than L plus epsilon. So this is just a very compact way of writing this. And there's nothing wrong, if you think about it, there's nothing wrong with fleshing it out this way. It's just that it's a little bit untidy. So mathematicians got together and said this would be a more convenient way to write the definition of limit. And again, what we're presupposing here is that in the general context, the C is approached from either side by X, like I wrote in the previous problem, but that might not always be the case. But in the general context, again, we have C, the value of X approaching C from either side, but remember the caveat, X does not equal C. So what we're looking at here, since this is a function, the tacit assumption is that X, the values of X here, actually are in the domain of F, but we're not saying anything about C. If we're approaching C, okay, from either side, then we're getting values of the function that make sense, but we're not saying anything about C being in the domain of F. So what we can do at this point is do our little number line like we had before. Let's put in our C. And then we have C plus delta. And then C minus delta. And then, of course, X is going to be somewhere in here. Now, of course, that we can put a little O here, a little circle, meaning that we don't actually hit the C. So X will be somewhere in here. Could be on either side. We just know that that's where X lives. And then, of course, you could think of this as being on the y-axis if you want. If we think of just the Cartesian coordinate system. So we'll mark off the L. And then the L plus epsilon. And then the L minus epsilon. And then, of course, the f of x somewhere in this interval. So what we can think of is that if X is in this delta channel, we can think of this as a delta channel. Then f of X is in the epsilon channel. And why does this definition work? Because now you can think of epsilon becoming arbitrarily small, okay? And so if the limit exists, regardless of the value of epsilon, as long as it makes sense with the function, you can find the delta. You can find the delta. That is, you can get close enough to C so that the value of F is within epsilon of L. So let's just say this in another way. If X is within delta of C, then f of X is within epsilon of L. So the idea is, this is just stating the delta channel and epsilon channel in other ways. If X is in the delta channel, f of X is in the epsilon channel. If x is within delta of c, f of x is within epsilon of L. So we are forced to think about this particular type of arithmetic only because with the previous example, all we did was just intuitively say x is approaching 0. And then we're thinking, okay, all right, so what do we do with this? I mean, how do we formalize this? And then you're thinking, wow, this problem is complicated unless we use some algebraic technique that we applied in our earlier courses. So there must be some way to say, okay, if we do a replacement, let me come back to this. If we do this identity replacement, that is, if we replace f with this function, that must be legal because, again, these two expressions are equivalent as long as we don't let x equal 0. Then if there is a limit and it's unique, it would have to be 2. And that's really what this definition of limit's going to allow us to show. So now we've already uncovered just intuitively that algebraic manipulations will allow us to replace a given function with an equivalent function for which understanding a limit may be much simpler. Okay, so again, even though this formal definition may be a little complex, it's simply working with absolute values. Again, using the conjunction, that is, if we throw out a positive epsilon, then we have to figure out how close x must be to c so that f of x is close to L. That is, if x is within delta of c, then f of x is within epsilon of L, as we've written here. Okay, so let's look at some more examples of this. Before we look at some instances where the limit doesn't exist, let's just get our feet wet, so to speak, with the definition of limit. Now, what we like to do is start with a simple example and then become more challenged as we look at more complex functions. But what we're going to do when we work into the next section is we're going to utilize the theoretical components of the definition to produce theorems that make the computation of limits much easier, because what we're going to see with the definition of limit is that working in the abstract, we can produce some fairly nice results. But if we have to apply the abstract definition to the computation of every limit, that would be quite cumbersome. We're going to find this to be a standard concept in calculus. We have a definition, and then we extract very elegant elegant theorems from those definitions to create a strategy and structure that allows us to do computations in a much more efficient way. Really, that's what calculus is all about and why it's never going to go anywhere. It's always going to be in existence because it describes what we see in our universe. And so if you want to do STEM, you want to do computer science, mathematics, engineering, finance, or whatever, calculus is here to stay. So let's look at a simple example. So let's look at the following. That is, prove the limit equation. So I'm going to write down the limit as x approaches 1 of the function 2x plus 3. Now, if you look at that, using the intuition from the last problem, you would feel very confident in knowing that that was equal to 5. That is, intuitively, if x is getting very close to 1 arbitrarily, very simple function, no radicals, then 2x is close to 2. Again, say 1 and a tenth, 1 and 1/100th, 1 and 1/1000th. If you're just approaching 1 from the right, 2x, 2. You add 3 to 2, you get 5. So intuitively, this makes sense. We could say this is intuitively clear. Now, of course, there are other things going on here that are telling us why this limit is indeed 5. Right now, basically, what you're thinking in your mind is you're just replacing x with 1 and you're adding 3 to 2 and getting 5. Well, there's a more probably strong mathematical reason for this being true. But intuition is always worth quite a bit in mathematics. So we will say more about that shortly. Now, let's look at this in terms of utilizing some arithmetic that makes this efficient. Like I said before, we're not interested in values of epsilon being very huge or whatever. So what we want to do is look at a neighborhood of 1 and use that as a way to, for instance, estimate if necessary. Now you're thinking, this is a very, very simple function. Do we even need to do that? But let's just think about this before we get started. We have 1, and then we have a neighborhood of 1. And we have a left approach, and we have a right approach. So we're doing something like this. And I'm not using pluses and minuses because I don't want you to think I'm doing some different kind of calculation or a sign test or whatever. I don't want to confuse you, so I'll do left and right. So when we look at this, we're thinking, okay, how can we use the definition to actually find a delta? Because we see when it starts out, you toss over to your professor an epsilon, and then your professor or whomever you toss your epsilon to has to come up with the delta. So let's just see what we have. So here's our proof. So we're just going to take epsilon positive. Then let's look at our function using the notation from the definition. So to the side here is a little sidebar. Let me write this down. We have c equals 1. We have f of x equals 2x plus 3. And we have L equals 5. So we could look at the epsilon channel. So f of x minus L equals, let's just go ahead and substitute. We have 2x plus 3 minus 5. Okay, so we're simply looking at f of x minus L because you gave me the epsilon. So I've got to work with what I've been given to see if I can work the definition in reverse to uncover some type of delta. And let's just see if what we have is sufficient. So now, of course, we just do a little bit of arithmetic. We have what? 3 minus 5 is a negative 2. So we get 2x minus 2. And of course, we'll have some opportunities to use properties of absolute value, which we will review as we work through this material. And so now, of course, this gives us 2 times x minus 1. And of course, the absolute value of a product is product of absolute value. So we just get the absolute value of 2, which is 2, times the absolute value of x minus 1. Now, what's nice about this is that we're thinking our delta neighborhood here is written in terms of 1. So in this case, this is where we have our little thought bubble. We have x minus 1 in absolute value less than delta. So this is the connection that we're looking for. We're thinking we did not have to restrict, as I said initially, to an interval about 1, because we're seeing that the absolute value of x minus 1 appears without any estimations. Okay, so now when we look at this, we're thinking, if we go back to the definition, the f must be within epsilon of L, and we have the epsilon. So this must be less than epsilon by definition. So if we just put a box around this and then move all the way here, we get something that's equivalent. Now, of course, we might have had to do some approximations on route here, but we're going to get a value for delta that will work. So now at this point, we're thinking, now how does this work? How can we choose the delta so this will work? Well, what we want to do is make sure that we absorb this. So a lot of students at this point just think, oh, well, I'm having to actually divide by 2 to get the value of delta. So notice here, if delta is less than epsilon over 2, then the absolute value of x minus 1 will be less than epsilon over 2, and that product will be less than epsilon. So this implies set delta equal to epsilon over 2. And everyone says, well, once I pick the delta, am I done? Basically, yes. You don't always have to go back and show that it works, but many mathematicians will do that. It's not always required. When we do proofs, once we get a delta, we're happy for it. And then sometimes we may go back and show off how it works, just to, flex our mathematical muscles. But at this point, you're thinking, okay, if delta is equal to epsilon over 2, then I will have x close enough to 1 so that 2x plus 3 will be within the epsilon of 5 that you've given me. Now, of course, this is in the abstract. So if you wanted to give us epsilon of 1, then of course delta would be equal to 1/2. So we could take specific epsilons and get specific deltas. But here's another thing that's important. There is nothing unique about any of this. The delta can be smaller than epsilon over 2 and still work clearly. So when students are like, well, I didn't quite get that, or I've got a different fraction or whatever, it doesn't matter. At this point, you could choose delta equal to epsilon over 10. That would still be less than epsilon over 2, which would still work. So just remember, when you're constructing a proof, your proof may not look exactly as a classmate's. It may not look exactly as your professor's. It doesn't matter. As long as the arithmetic is legitimate, then you can always refine things. We're going to find out that we are simply looking for estimates that make the arithmetic correct. And so when you think about limits, there's a large amount of flexibility. So this would be our selection or a selection. Just remember, any positive delta less than epsilon over 2 will work. So you can always refine it. You just don't want to get any bigger. That's not going to work. But Refining it will always be the case. So now we have everything set up the way we want. So we could say, here's like the punchline. Take epsilon greater than 0. Then set delta equal to epsilon over 2. Therefore, if x minus 1 is less than delta, so we just say less than epsilon over 2, then, oh, and let me get my absolute value in there. Sorry, I left that out. Then I'll just do what I need, 2x plus 3, and I'll do it kind of formally, put that in parentheses, minus 5, which equals, just skip all of that, we know it's true, 2 times x minus 1. But we have an upper bound on the absolute value of x minus 1. So this is greater than 2 times epsilon over 2. And of course, the 2's absorbed, and we have epsilon. So this part is just basically checking. It's like checking your answer to an equation. Once you determine an appropriate delta, then you're done. You can do this as a way of just verifying that you have something that's correct. But to get to this, you have to do the estimates here. And so this is just a way of, just like I say, writing the punchline and putting it down in a very clear format. But be aware that once you have the delta, you are good. And any value here that is less than epsilon over 2 will also work. So you can refine it as long as you're moving to values that are less. So you might be thinking, okay, probably wouldn't be very convenient to have to do this for every type of function, especially if the function got more complicated. But just remember, the key is this. A positive epsilon is given. That creates an epsilon channel. And you're thinking, if I'm doing the definition, I've got to have at least this. I've got to have the C, I've got to have the function, and I've got to have the L. That is the assumption of a limit. If you're proving the limit equation, okay, then the assumption is that the limit equation is true. And so you've got all the pieces to work with. And you use those pieces to work your estimates. Now, just by looking at this, you can see in the abstract that this is very powerful, and we're going to be able to produce some really nice theorems. Now, in some cases, the limit theorems can be difficult. In other cases, they can be very straightforward. But the essence of doing any of them is just sticking to correct arithmetic and making solid decisions. So let's try another one with this. Just up the level of difficulty just a little bit. So let's look at this example. So prove the limit equation. Now, of course, there'll be examples in the homework where you find a delta, because just like I said before, if you're given a specific epsilon, you can get a maximal value of delta. Like I said before, if you were given epsilon equal to 1, then you could take delta equal to 1/2. So you can do your problem in complete abstraction and then supply a particular value of epsilon, or the problem may give you that value and you just find the delta using basic inequalities with absolute value. So let's prove the limit equation here. So we're going to have the limit as, we'll keep it simple, x approaches 2 of x squared plus 3. Now, of course, we can work with quadratics, but we have to work a little bit harder. So what I want to do is just at least give you examples where there may be some need to do more estimations, that is, create some kind of delta neighborhood about C before we move on with the computations. And what you're going to find is that when you look at the inequalities, we're just going to need to make some estimates, because there'll be part of the inequality that has factors that need estimating. And I'll show you how the example kind of pushes you in that direction. Now, of course, in this particular case, we would know that this limit would be 7 if we use the basic intuition that we've been using all along. So now, when we look at this, we say the limit as x approaches 2 of x squared plus 3 should be 7, because we're thinking, okay, square 2, we get 4. 4 plus 3 is 7. We're thinking, yeah, this should be correct. Now, again, later on, we won't think 5 seconds about a problem like this. We're going to use what we call limit theorems for polynomials and say, I'm done. Direct substitution, okay? And you're going to find many limits are very simple to compute. And you're going to think, wow, I could have done this in college algebra. Now, there are parts of calculus that are very simple, okay? Extremely simple. But the majority of it isn't, in the sense that in Calculus 1, you build the foundation so you can do Cal 2 and do Cal 3, and then your PDEs and your differential equations and differential geometry. So calculus is going to be the bedrock of everything that you take after this. So now let's do the same thing. Notice, we'll go ahead and do the sidebar. C equals 2. F of x equals x squared plus 3. And the limit is 7. So these are all the parameters that we need when we do our calculations. So let's do our proof. Now, like I said before, you heard me mentioning that we might need to have an interval about 2 for our estimations. And just for grins, I'll go ahead and set that up. But I don't want you to think that if you didn't, you would be in trouble. It's just that if you let that out, you would find the need to go back and do it. So don't worry if you leave out a particular estimation. What you're going to find with limit theory is that as you apply a certain technique, you'll have to go back and kind of look, where do I need to go? What do I need to understand? How can I make this process work? And that may take a lot of intuition. But as you develop that intuition, you can use it over and over and over. It's so surprising, and not surprising in mathematics, that you can use good techniques often. So just to make life simple, here's what we're going to do. We're going to restrict. So in this particular case, let's just first take epsilon positive. And in this particular case, let's have a very simple neighborhood for x. Let's be on one away on either side. So we'll say x will be in the interval 1 to 3. So let's just do a little diagram of that. And this is completely arbitrary. This is what I was talking about before. Your arithmetic will look different if you make different estimations here. So we're going to say that we have 2 here, and then we're just going to restrict our approach like we did in the very first example to this. So we have our left approach, and we have our right approach like this. So we're just saying that when we are looking at this particular situation here, we are allowing x to approach 2, but in a restricted interval. Maybe we don't need this. Maybe this is just extra. That's what we're doing. So now with that, we'll keep that in mind as a way to make estimates. So just remember the distance here between 2 and 3 is 1. The distance between 1 and 2 is 1. So that's basically saying a delta equal to 1. And can we improve upon that? Okay, so let's move forward. Now, let's look at f of x minus L. So we'll go ahead and fill all this in. So we have x squared plus 3 minus 7. Now, of course, this simply just ties the definition to the particular problem. That's the only reason I'm doing that. And so now, of course, 3 minus 7, that gives us a negative 4. And now we have a difference of 2 squares. So we have x minus 2 times x plus 2. And now, of course, we use the same theorem about absolute values. The absolute value of a product is the product of absolute values. Now, of course, this is very convenient for the definition of limit x minus 2, but the x plus 2 is something that we need to think about. So again, we're going to have another sidebar here. Notice we have this particular inequality here. So we have 1 less than x less than 3. That's where x lives. So let's figure out where x plus 2 lives. So now we can add 2 everywhere. So we have 1 plus 2 less than x plus 2 less than 3 plus 2. So now we have 3 less than x plus 2 less than 5. Oh, and sorry, I don't have this yet. So we have x plus 2 living between 3 and 5. Now, when we think about this and we think about absolute values, this is very important. Notice, and this is essential to this particular problem. The value here is positive and the value here is positive. So this implies that the absolute value of x plus 2 must be less than 5. So that's the implication we have here. So this implies that the absolute value of x plus 2 is less than 5. That's very important. So we can't just jump to the absolute values until we look at the sign of these particular numbers here that bound the argument x plus 2. So now we look at this and say this gives us an estimation. So here we have what? Less than x minus 2. And then we have an upper bound of 5, so we can have times of 5. So this was just like before when we were working the problem. This is the x minus c, which we need. Now, of course, from the definition, using this estimation that we have for the absolute value of x plus 2, we now need this to be less than epsilon. So this is the key. What the goal is to find the x minus c times some number, or it might be times several numbers that we have, that we know. So the idea is, can we control the size of f of x minus L? The answer is yes. So now what does this do? Let's just take another color. This implies set, just like we had before, delta equal to the minimum of, well, again, we need the epsilon over 5, or the 1 that we have here. Remember, notice the distance between 2 and 3 and 2 and 1 is 1. So we've got that. So why is that important? Well, when you take the minimum, that gives you that. The fact is that the minimum here will always be less than epsilon over 5. So if we want to use that in an estimate to make our punchline look right, we're fine. But the key is here, say you take your epsilon equal to 1 as a specific, value, you get, in this case, 1/5. That is the smaller. But say you chose an epsilon of 10. Okay, then you got 10 over 5, which is 2. The smaller value is 1. So you would have to choose the 1 for your estimates to work. So when you do a more complicated function, you will necessarily be required to make estimates. So that will, again, require you to restrict the approach to C. In this case, the C is 2. So now we have a way to what? Select an epsilon. So now we can just, here's the punchline if you want to write it, punchline. So we say take epsilon positive. Then set, I'm just repeating myself, delta equal to the minimum of epsilon over 5, 1. Therefore, f of x minus L equals x plus 2 plus 3 minus 7. So just kind of skip to the punchline. That gives us x minus 2 times x plus 2. And then, of course, we can use our 5 less than x minus 2, little space for my minus sign, times a 5 less than epsilon over 5 times 5, which equals epsilon. So whatever value we have here, it will be less than epsilon over 5. So we can use this as an upper bound. So the arithmetic looks good. So in our estimate, we simply emphasize the fact that if we need an upper bound here for x minus 2 in absolute value, it'll clearly be this. But the key that's important here is that since we have a more complicated function, we have to make a restriction on the approach. And this allows us to pick the appropriate delta when we're doing our proof. So just remember, in the last problem, it was fairly simple. When we do our absolute value arithmetic, we only have the x minus c in absolute value times a constant, so we don't need any additional estimation. Here, we had a more complicated estimation with the absolute value. We've got the x minus c in absolute value, but we have this additional term here, which we can easily take care of by restricting x to be in a particular, and we were very convenient here, a symmetric interval about 2. Notice all of these intervals in the definition are symmetric. We have the delta neighborhood of C, symmetric interval. We have the epsilon neighborhood of L, symmetric interval. So the key, and again, this is very important, once you select the delta, you are done. Once you have a rule for selecting delta, then you are complete with the problem. You don't have to, the punchline is fine. It makes everything look good. It's like checking your answer when you solve an equation. But the key here is think about the definition. For the epsilon positive, there exists a delta, so that if x is within delta of c, f of x is within epsilon of L. So the key is finding the delta. And of course, what we see here, the delta is not unique. There's the flexibility there. So what's important here is just realizing that the definition is actually a friend to you. It's not overly abstract. You simply let the inequalities tell you what you need to do using some very straightforward applications of absolute value. One nice thing about calculus is that you learn a whole lot more about absolute value, and you get to use those interesting inequalities from college algebra and pre-cal that usually never found their way to anything except an academic exercise. So now you have a reason for having studied these, because all these symmetric intervals make this particular study very efficient and easy to write. And then you can say that we have these very interesting ways of saying x is close to c and f of x is close to L in a very precise way. Now, one thing I want to talk about, because as we get into the next section, we're going to focus on how the limit definition gives us very nice theorems to compute limits. But I want to just say a few things about limits that don't exist. So let's just look at some of these. We'll just say limits that do not exist. So there's no reason to believe that a limit exists, and there's certainly no reason to, at this point, the limits are unique, but we haven't proven that, and that's not really difficult to show. But for right now, when you compute a limit of a real valued function, or it could be complex valued, it doesn't matter. The limit is unique. Okay, and we'll say more about that. But the existence of the limit is not guaranteed. So let's look at some situations where that might be the case. So we'll start out with something having to do with trigonometry. Then we'll do some easy ones to end up. I want you to be comfortable with the definition of limit. I don't want this to be overly abstract. I'm trying to keep the arithmetic simple and, again, have a reason as to why we do all of this work. So let's look at something like this. For instance, this is nicely done in most textbooks in calculus. So we're going to say x is approaching 0 of sine of 1 over x. Okay. Now, this is going to require some intuition, but it'll be worthwhile intuition. So what I want to do is to consider your unit circle and values on the unit circle that provide sign values, or points in the unit circle that provide sign values of 1 and -1. And when I say points, I'm thinking about distances along the unit circle, of course, that terminate where the sign is actually, or the y-coordinate is 1, and where the sign is -1. So here's the observed part. So for instance, if we think, in this case, let's just do some congruence. So we'll say 4n plus 1 pi over 2, look like that. So this is congruent to 1 mod 4. this gives, and I'm just going to say in this case, x equals that value, and I'll just say n is an integer, then this gives a sine value of 1. So we'll say sine of x equals 1. And if x is equal to 4n plus 3, that is congruent to 3 mod 4, then we're in the lower part of the unit circle. This gives sine of x equal -1. So you think pi over 2, 5 pi over 2, 9 pi over 2, 13 pi over 2, that always gives a sine of 1. And then if you move down, 3 pi over 2, 7 pi over 2, 11 pi over 2, 15 pi over 2, things like that give you the -1. So now what we want to do is flip it around. So in this case, when we look at this and we're thinking, how can we do this so that now if we have a value of x and then we reciprocate it, how is this going to work? So this implies now, so this is the observed part. This is just kind of thinking outside the box. So now set for the first part, number 1. Well, let me not give this a number. Well, I'll give it a number and then I'll change what I've written here so it doesn't look confusing. Let's call this just little I. So we're going to say x sub n, notice I've got the n here, will be, we're going to reciprocate everything. So we're going to say 2 4n plus 1 times pi. And then for the second part, we're just going to use another sequence. We can just call it, I don't know, give it another name. We'll just say y sub n 2 4n plus 3. And so now when you reciprocate these, so that we're using what we've done up here. So this implies sine of 1 over xn, which is going to give us exactly this, will be 1. And then sine of 1 over y sub n will give us -1. Okay? So I remind you of the unit circle, and then I remind you of this. Now, here's the key, and this is why this works. Intuitively, what's going on here, as the values of n get larger and larger, and notice we're going to be approaching 0 from the right, just because this is a simple method of showing that no limit exists. We observe or note, and this is very intuitive, that the limit, thinking of just what we did in pre-cal, even though I'm kind of pushing the limit, no pun intended, here, x sub n. So now we notice that the 2 is fixed, and if n becomes arbitrarily large, then the denominator becomes large relative to the constant numerator. And so intuitively, we would think a limit of 0. And the limit in this case, I'm sorry, math is always self-correcting, n approaches infinity. And here we have n approaches infinity of y sub n would also be 0. So what we're seeing is that these sequences have limit 0, at least intuitively. We'll prove more about this when we get later on in the course. We talk about limits at infinity. So intuitively, what's happening is that both of these are approaching 0. Okay? So in this case, we can now say, so this implies the limit as n approaches infinity of sine of 1 over xn equals 1, just using this, because all these values are 1, even though the particular sequence is approaching 0, all the values give 1, and the limit as n approaches infinity of sine of 1 over yn is -1. So what's interesting here, and this is when I say this is a good example, it's somewhat complicated, but intuitively, this is where you use your pre-cal and your trig to actually make sense of all of this. So what we're seeing is both of these sequences are approaching 0 from the right. That is, these are approaching 0 through positive values. But every time we apply the function to the reciprocal, in the first case, we get a 1. But if we apply the function to the reciprocal in the second case, we get -1. So again, using the premise that limits are unique, we are at an impasse. So we get closer and closer to 0 from the right. In some cases, we're going to end up at 1. In some cases, we're going to end up at -1, but that will never retire. So you can get closer and closer and closer to 0, and you're still going to get infinitely many values of 1 and -1. So in this case, this implies that the limit as x approaches 0, now back to the original notation, so we have to change notation to work this, does not exist. Now, this is a more advanced idea, but the idea here is we're looking at sequences, and you've only had limited work with sequences from pre-cal. But the idea is that if you can take a sequence that has an approach to 0 and show that the values of the function are always 1, and then take another sequence that is also approaching 0, and these are both from the right, where the values are always -1, then it's like the function can't make up its mind. So again, the limit is unique. And so when we look at something like this, we say the limit does not exist by oscillation, because you've got a value 1, -1, and there are infinitely many copies of those as you get closer and closer to 0. And a lot of times as you start to graph this, if you use a fancy graphing calculator, which I don't allow you to use in this course, but the idea is that the graph becomes just a smear of black because the oscillation goes wild. So again, if you are trying to figure out whether or not a function has a limit, and you're at an impasse and you're thinking, wait a minute, let me look at a sequential argument. Let me think of some sequences from the unit circle and use a little bit of logic and see what I can do. So you think about what you learned in pre-cal, and then you flip it. So this reciprocal makes sense. And so by using sequences that approach 0, we show that the limit doesn't exist. Again, the limit must be unique. So this is a very, very important strategy of showing that limits don't exist, which turns out to be a direct use of your pre-cal. So take this example and work with it some. It's actually part of your textbook. As you read through the text, you'll see this, but they don't flesh this out very much. It's like fairly scant. So what I decided to do was add a little bit more detail to this so you can actually see why the limit doesn't exist. And there's a fair amount of intuition here, but because we haven't covered limits at infinity, we're just starting. But the intuition here is telling you that if limits are unique, then there's no way that a limit could exist here, because again, the function values repeat infinitely many times, and there's no convergence, as we say, to a unique real number. Now, the last example that I wanted to show you is much simpler. And you're thinking, why didn't I start with this? So let's look at this example. So we have f of x. We'll have a function defined in pieces, a real simple one. Say we have x equals 2 when x is greater, well, let's just say less than or equal to 1. And we'll say -2 when x is, say, greater than 1. Okay, so the key here is that we have to do like an epsilon channel, right? So we're thinking if we approach 1 from either side, if you throw out an epsilon, I should be able to give you a delta that'll make sure that if x is within delta of 1, f of x would be within epsilon of what? 2 and then -2. And you're thinking, okay, let me see. This is going to work. Okay, so we'll just say this. Limit as x approaches 1 of f of x. We'll say prove the limit does not exist. So when you look at this, you're thinking, okay, well, if I think of what the picture looks like, would that give me some intuition? So let's just look at a picture of it, because it's real simple. I mean, even though a picture is not a proof, let's just see if it gives us some intuition. So here we've got 1, and then we've got 2, and we've got -2. So, at 1, we can do a little dot there. Do this. And let me just kind of do like a little blue here. And then at 1 greater than, we'll have a circle. We'll have this. So the idea is that we need, if you throw out an epsilon, I should be able to get a delta. So let's just think of this. Here's a simple proof. So we're going to say, in this particular case, set will be real specific. Epsilon equal to 1/2. Okay, epsilon equal to 1/2. And what we're going to do is we're going to look 2 cases. So first, case 1. We're going to let x, just say x live here, and we'll just do, say, 0 to 1. Okay, so when we look at that, we're like, okay, for 0 to 1. And then we look at f of x minus L. So here, when we look at this particular case, the only option for the limit would be 2. So I'll put this in red. I'll just say, in this case, L equal 2. So we have, in this case, on this side, we have 2 minus 2, which equals 0, which is always less than 1/2. So in this case, delta positive. And so that would be arbitrary. That'd be nice. That's nice when you got something constant. That's easy. Delta can just be any positive number. Now for case 2, we have, we'll just take x between 1 and 2. So on this side. But then, of course, if that's the case, L equals -2. And that's the problem. That's the problem. We can fit it. So now, of course, if we do f of x minus L, this gives us -2 minus the negative. That'll be +2, which is 0, which is certainly less than 1/2. But in doing these two cases, we don't have a unique limit. So you're thinking, okay, if we were just looking at the approach from the left, 2 would be the limit. If we were just looking at approach from the right, -2 would be the limit. But if we're approaching from both sides, there's no way there's no way to work it, because again, if we choose this limit to work down here, then we've got what? We've got 4, and we're like out of the water. So if we use the limits that are prescribed by the characteristic of the function, then we're forced to have a non-unique limit. Because if I say it's 2, it won't work here. If I say the limit's -2, the inequality doesn't work here. That is, this number would be much bigger than 1/2. So what we've shown in this particular example, and this is going to be something that we do later in the course, is that the limits from either side actually exist. But the standard limit approach from both sides doesn't. So this implies, in this case, the limit as x approaches 1 of f of x does not exist. Because, like I said before, if you assume that 2 is the limit, it doesn't work here, and vice versa. So when we're just looking at the cases and we think about what the function looks like, we're forced to have a different limit as we approach from either side. So as I said before, the left limit would exist, the right limit would exist, but they're not equal. And using the fact that I've said before that limits must be unique, it's not like a completely lost cause. It's just basically saying that the actual limit existing from the standard case must exist from both directions. And when that's not the case, you're still not completely out to lunch. You may have a left and a right limit existing. Now, there are other instances where we have limits at infinity, where you can read about where a particular function becomes unbounded. And let me just say this, limits are real numbers, okay? We can say later on, we're going to talk about infinite limits, like the function becomes infinite, like 1 over x as x approaches 0 from the right. For instance, in pre-cal, we had something like this. And this is notation I haven't introduced, but if we approach 0 from the right using a little plus, we would say that's infinity, because the particular function becomes arbitrarily large, and we need to show that arithmetic. But that's not a real number. So we would say in this case, limit does not exist. And that's like, okay, well, that's really messed up, Professor Ollis. It's like, wait a minute, that's a right limit. We haven't really talked about that. So what I'm saying is that you could change it up a little bit. You could say the limit as x approaches 0 of 1 over x squared. That's infinity also. So you're thinking, that's more like a standard limit, and that's not a real number. So this doesn't exist either. So limit does not exist. So when we think about limits, we are really kind of forced to say, okay, when we look at the standard limit, we have approach from both directions, left and right. The limit is unique, and the limit is a real number. Okay, so what we're seeing is if we're forced to choose a different limit when we have approach from right and left, that's it. There's no existence of the standard limit. But the right limit and the left limit exist singularly. Now, again, even though we're going to talk about infinite limits as being characteristic of the function, they're still not standard limits. So when we look at things like this, we're going to be very interested in understanding the arithmetic of infinite limits in the sense of function becoming unbounded. But in the critical sense of the limit, that's non-existing. So just remember, this process is made simple by looking at the graph. Even though that's not a formal proof, you have to look at the cases. And of course, we're forced to pick different limits for the definition to work, so there is no limit. And then, of course, in the most complicated case is where we look at sequences that both approach 0. And so by virtue of the fact that these sequences approach 0 but give different values of the function, all bets are off too. So even though this is a little bit more complicated, the intuition should be there. So what we'll do next time, ladies and gentlemen, is we'll investigate analytical methods for computing limits that will make the process very simple, but we're going to drag along all of the intuition that we've set up because it's very important. We'll never formally leave any of this information. It's going to come with us as we continue through the course, as you work through the calculus sequence and on into engineering classes that use mathematics, other mathematics classes, you name it. Physics especially. So just remember, the time you spend now to build your intuition and your arithmetic will be very much worth it. So we're done. So we'll see you next time.